The next question of lead code weekly contest 380 is find beautiful indices in the given array 2.
In this question, we are given with three strings, string S, string A, and string B, right? Along with that, we are also given an integer k, right? What we are supposed to do is we are supposed to find beautiful indices of this string S. Okay. Now, what is a beautiful index? A beautiful index I is nothing but I ranges from 0 less than or equal to I less than or equal to S dot length minus A dot length.
Yeah.
I is any index which ranges from 0 to S dot length minus A dot length. And in this index, when we choose a particular I, then the substring starting from ith index all the way up till I plus A dot length minus 1 should exactly be equal to string A.
Yeah.
Basically, when we choose an index I, from that index I, the substring that is formed should exactly be equal to string A.
Yeah.
Right? Now, when we choose such string I, such index I, there will also be an index J. There will also be an index J such that 0 less than or equal to J less than or equal to S dot length minus B dot length. It means J is an index which is in interval 0 to S dot length minus B dot length. And when we choose such index, then the substring formed from index J all the way up till J plus B dot length minus 1. If this is exactly equal to B, this is exactly equal to B string, and if J minus I has a modulo difference of less than or equal to K, then we can say that I is a beautiful index.
Yeah.
Like this, we want to find all the beautiful indices and print them in sorted order.
Yeah.
That is the question. Looking at the constraints of the question, we are given that K will be in the range of 1 to 5 into 10 power 5. This is the range of K given. It is also given that K will be less than or equal to S dot length.
Yeah.
And coming to our A length and B length, A length as well as B length will be in the range of 1 to 10 power 5. 1 to 5 into 10 power 5.
Yeah.
And it is also given that string A, string S, and string B all contain lowercase English characters.
Yeah.
These are the constraints.
So, firstly, let's look at the prerequisites of this problem. So, prerequisites for this problem are you should either know one of these KMP algorithm, or Z-algo, or string hashing. Basically, you should know you should know some algorithm where you can do string matching with it. So if you know either of these, it's sufficient. Uh, and you should know binary search, and two pointer. Even this is a prerequisite. We can either do it with binary search or two pointer. So any one of them you should be. So these are the prerequisites. Now let's see how we can solve this problem. So basically in this S is the original string. Right? So let's consider the indices of S 0, 1, 2, 3. So in each index, a character is given. Right? And let's consider A. A is the given string. and B is the given string. Right? So here, as per our conditions, first condition for I to be beautiful is from I in the substring S I till I plus A dot length minus 1 should be equal to A, right?
Yes.
This is first condition. J comma J plus length minus 1 should be equal to B. This is the condition for J, right? So now, and there is additional condition, that is mod of this should be less than or equal to K, and K is also given for us. So now this is our additional condition. Firstly, let's focus on these two conditions and find out all I and J points which satisfies this. So for that what we can do is we can perform string matching. That is, we have S, right? So in S we can use any one of the string algorithm mentioned, either KMP or Z or string hashing, and find out in from how many positions will a pattern occur. So basically with those string algorithms, we can get the ith value, I value, where all the pattern matches. So let's say A is present as a substring over here, then for this one will be the I, right? Because that is the starting point. So using those algorithms, we can just deduce the starting point, just perform a Z function. Let's say if we are using Z function, then perform a Z function, and we'll be creating a Z array in Z function, right? Using the Z array, retrieve all the indices starting from that index. If we consider the substring of S starting from that index, that is equal to retrieve all such indices, because those can be our I values, right? So firstly, deduce all those I's which satisfy this condition, all I's, and we can apply exactly same thing to deduce J's also, right? All J's. So even for J's, use any string matching algorithm, and now the pattern is B for us. Using B, find out the start indices of the substrings which are equal to B in S, and let's say we got all such indices. Now basically we have all I indices, right? Now basically we came down to a simple problem, that is we deduced all I's and J indices. So let's say these are some values of J, so we can just name it as I1, I2, I3, I7. All these are I indices which are satisfying the first condition, right? And now all these are J indices which are satisfying the second condition. Now we handled first two conditions, but we didn't handle this, right? So to handle this, we should make decision on I, right? Because we need to output all I, all indices I which are beautiful. For I to be beautiful, firstly these two should satisfy, and this should satisfy, right? These two we already handled. For a particular I, for it to be beautiful, there should exist at least one J such that mod of absolute of I minus J is less than or equal to K, right? So now what we'll do is we can just sort I and J's. Sort J's also. And now assuming they are in sorted order, for I1 to be our answer, assuming I1, I2, I3, they are in sorted order, and J's are also in sorted order. Now, for I1 to satisfy, for I1 to be beautiful, it should satisfy this condition, right? So for it to satisfy this condition, can we say that it is always optimal to check for two type of J values? One J value can be the floor value and other can be the seal value from this J. Now let's see what.
Basically, we are looking for the closest value of J,
Yeah.
which is
Near
as
to
close to I1 as possible.
I1 as possible.
Right? And to find the closest value of J, which is as close to I1 as possible, will be either finding which is exactly equal to I1, or which is we'll be finding an element which is
floor of
I1 or seal of
I1.
These are the only three values which will be as close to I1 as possible.
As close to I1 as possible. So basically, floor is nothing but finding out the J value, which is just smaller than or equal to I1. Right? And seal is nothing but finding out J value, which is greater than or equal to I1.
Yes.
So now this is smaller, less than or equal to I value. This is greater than or equal to I1.
Yes.
Just greatest. So closest one which is smaller than or equal to I, closest one which is greater than or equal to. So now to find this floor of J for a particular I, we can binary search and find that out. And similarly, we can binary search and find out seal also, as J is already sorted. Or we can either use set, we can put J in a set and use lower bound and upper bound functions of set. Or we can even do it with a 2-pointer. But ultimate goal is to find the floor of J and seal of J. No matter what we use, we just need to find out floor of J and seal of J.
I think we will be finding floor of I in this J array.
Floor of I in the J array.
Yes.
So floor of I in the J array. So yeah. Floor of I in J will be finding out. And seal also in J array. So this is how it is written. So now let's see. Now we are just performing binary search to find these out. And in case we'll just try it for floor, I minus the floor value of I in J. Either this should satisfy the condition or I minus C. Or either this should satisfy the condition. If any one of them satisfies, then we can say I is beautiful. As taking values lesser than floor is useless because the difference will increase if we take less than floor. Similarly, taking values greater than seal is also useless as difference will increase even in that case. So this can be the smallest differences that we could get. So we are testing if the smallest differences that we could get itself is less than or equal to k. If they are itself not less than or equal to k, for sure distances greater than that won't be less than or equal to. So this way we can just solve the problem. So if you look at the time complexity, we can say it is time complexity is s dot length plus a dot, where s is the original string and a is the pattern. This is when we perform z or kmp for a, considering a as pattern, plus again performing z or kmp assuming b as the pattern. It would be s dot length plus b dot length. This is for the second kmp or z that we use. And now we have the indices. Right? So now on this indices, we are basically performing binary search. So while getting these indices, we need not. It depends on how we implement. If we pick these indices in order, then we need not require to sort them. Right? But if you don't pick them in order, then we should sort. So assuming we already picked them in order, then because we are performing a binary search, we can say it would cost us, in the worst case, can we say it is h dot length? It won't be exactly h dot length, but something equivalent to h dot length. So we can say it's h dot length log of h dot length, right?
Hmm.
In the worst scenario.
Yes.
So if we perform a binary search or use a set, it would be this. Or if we use a two pointer, we can just do it in h dot length time complexity. So h dot length into log base 2 of h dot length or h dot length, both are allowed here. So this is sufficient enough to pass in 1 second of TL also. If we look at the space complexity, we can say the space will be a dot length. Assuming we are performing z or k, then it would be h dot length plus a dot length plus b dot length. This would be the space. And we can even optimize the space to big of 1 using string hashing. But this is sufficient enough to pass the given constraint. Sufficient enough to pass the question in the given T with given constraints. So these all are purpose.